Welcome. In designed experiments, we spend a great deal of effort computing effect estimates, but an estimate alone is only half the story. Today, we close that gap. We are going to move from a raw point estimate to a defensible conclusion, one you can hand to a client, defend in a review, and act on with confidence. The path runs through standard errors, t-tests, a formal decision rule, and a disciplined model reduction. Every concept will be grounded in a single running example that we carry from the first slide to the last. Let me start with a principle that sounds obvious but is violated constantly in practice. An effect estimate by itself is incomplete. If I tell you that raising reaction temperature increases tensile strength by 9 units, you cannot yet decide whether that matters. 9 units relative to what uncertainty? The result only becomes decision-ready when you pair it with its standard error. The formula is simple. Your result is the estimated effect plus or minus its standard error. That pairing does two things. First, it separates signal from noise. A large effect with a large standard error may be indistinguishable from zero. Second, it gives a client what they actually need, not just how big, but how reliably big. Magnitude and uncertainty together drive decisions. Neither alone is sufficient. Here's the study we will work with throughout this lecture. A polymer manufacturer wants to understand what drives tensile strength in their product, measured in megapascals. They have 3 factors under their control: reaction temperature, which we will call A, catalyst concentration, which we will call B, and mixing time, which we will call C. Each factor is set at 2 levels, a low level coded as -1 and a high level coded as +1. The design is a full 2 to the 3 factorial, meaning all 8 combinations of the 3 factors are tested. Critically, the entire experiment is replicated twice, giving 16 observations in total. This replication is what will allow us to estimate pure experimental error from within the design itself. No assumptions about which effects are negligible. No external error estimate needed. Let me walk you through the actual data. We have 16 runs. Each row records the coded levels of temperature, catalyst, and mixing time, which replicate it belongs to, and the measured tensile strength. In the first replicate, the 8 treatment combinations give strengths ranging from 37.4 up to 55.1 megapascals. In the second replicate, the same 8 combinations give strengths from 34.2 up to 56.4. You can already see that the combination with temperature high and catalyst high, runs 4, 8, 12, and 16, consistently produces the highest tensile strength. The combination with temperature low, catalyst low, and mixing time high, runs 5 and 13, sits at the low end. This is the dataset we will carry through every concept today. Hold it in mind. Now let us build the formula for the standard error of an effect estimate in a replicated 2 to the k design. Every effect estimate in this design is a contrast, a weighted sum of all n observations, where n equals n times 2 to the k, and n is the number of replicates. Because the contrast uses +1 and -1 weights, a factor of 4 appears in the variance formula. Specifically, the variance of any effect estimate equals 4 times sigma squared, divided by n times 2 to the k. Taking the square root, the standard error equals 2 times sigma, divided by the square root of n times 2 to the k. 3 things to notice. First, the factor of 4 is not arbitrary. It comes directly from the +-1 contrast scaling. Second, variance shrinks as total runs grow, which is why replication pays off. Third, and most importantly for practice, sigma squared is unknown, and the only internal estimate of it comes from the replication. That estimate is the mean squared error from the ANOVA table. There is no other source of pure error in a single unreplicated factorial. which is exactly why replication is so valuable. Let us apply this to the polymer data. We fit the full model, all 7 effects, 3 main effects, 3 two-factor interactions, and a 3-factor interaction to all 16 observations. The ANOVA table from that fit gives us a mean squared error, which is our estimate of sigma squared. We then plug that MSE into the standard error formula, SE equals 2 times the square root of MSE divided by n times 2 to the k. In our case, n is 2 and 2 to the k is 8, so n times 2 to the k is 16. The formula becomes 2 times the square root of MSE over 16, which simplifies to the square root of MSE over 4. 1 MSE, 1 formula, 7 standard errors, all identical because the design is perfectly balanced. Here are the results. The 7 effect estimates and their standard errors are laid out in a table. Temperature, factor A, has an estimated effect of 9.72 megapascals. Catalyst concentration, factor B, comes in at 7.35. The A-B interaction is 5.46. Mixing time, factor C, is 1.27. The AC interaction is 1.77. The BC interaction is 1.3. And the 3-factor interaction is negative 0.91. Now look at the standard error column. Every single entry is 0.739. This is the elegant property of the balanced 2 to the k factorial. One standard error characterizes the precision of every estimate in the table simultaneously. You compute it once, and it applies everywhere. Already, you can see that A and B are large relative to their standard error, while C and the higher order interactions are much smaller. But we need a formal test before we act on that impression. Before we run those tests, I want to make a point about reporting that matters enormously in practice. You will often see experimental results summarized only as an ANOVA table, a column of sums of squares, F statistics, and p-values. That table is useful for significance testing, but it destroys 2 critical pieces of information. The sum of squares for an effect equals n times the squared effect divided by 4. The squaring does 2 things. It removes the sign so you cannot tell whether raising a factor increases or decreases the response. And it compresses differences in magnitude, so 2 effects that are very different in size can produce similar sums of squares. A client who needs to decide whether to raise or lower temperature cannot act on a sum of squares. They need the effect estimate and its standard error. Report both. To make this concrete, let us place the effect estimates alongside the sums of squares for the polymer experiment, so you can see exactly where information is preserved and where it is lost. Here is the comparison. Temperature has an effect of 9.72 and a sum of squares of 378. Catalyst has an effect of 7.35 and a sum of squares of 216. Now look at mixing time and the BC interaction. Their effects are 1.27 and 1.13, close in magnitude, and their sums of squares are 6.45 and 5.08, also close. So far, the 2 columns tell a similar story. But consider the AC interaction, effect of 1.77, sum of squares 12.5, and the AB interaction, effect of 5.46, sum of squares 119. Those 2 effects differ by a factor of 3, but if you were only scanning the SS column for patterns, you might not appreciate how different they really are. The ANOVA table is a significance filter. It is not a communication tool. When you report to a client who must decide whether to change a process setting, the effect estimate and its standard error are what they need, not the sum of squares. Now we formalize the test. Under the standard assumptions, normally distributed, independent errors with constant variance, each effect estimate divided by its standard error follows a t-distribution. The degrees of freedom are those of the MSE, which comes from the replication. So the test statistic is simply the estimated effect divided by its standard error, and we compare that to a t-distribution with the MSE degrees of freedom. There is an important algebraic connection here. When a factor has exactly two levels, the square of the t-statistic equals the f-statistic from the ANOVA table. This is not a coincidence. The two tests are mathematically identical. But the test gives you more. It preserves the sign of the effect, so you know the direction of the relationship, not just whether one exists. In practice, always report t-statistics alongside or instead of f-statistics for factorial effects. Let us verify the t-squared equals f relationship on the polymer data. We extract the t-statistics from the fitted model and the f-statistics from the ANOVA table. Then check that squaring each t reproduces the corresponding f. Here are the numbers. Temperature, t-statistic of 13.2, t-squared of 173, f-statistic of 173. Catalyst, t of 9.95, t-squared of 98.9, f of 98.9. The AB interaction, t of 7.39, t-squared of 54.6, f of 54.6. f of 54.6. The equivalent holds exactly for every term in the table. Now notice the signs. The three-factor interaction has a t-statistic of negative 1.23. The f-statistic is 1.52 positive, as f-statistics always are. If you only had the ANOVA table, you would not know that the three-factor interaction, whatever its magnitude, points in the negative direction. For a process engineer deciding whether to simultaneously increase temperature, catalyst, and mixing time, that sign is not optional information. Report t-statistics. Before we look at the formal decisions, I want to be precise about the testing protocol, because this is where practitioners most often go wrong. We are running 7 simultaneous hypothesis tests, one for each effect. Each test asks, is this effect distinguishable from 0? We reject the null when the absolute value of the t-statistic exceeds the critical value, which is the t at alpha over 2, with the MSE degrees of freedom. The critical discipline here is that alpha must be fixed before you examine the results, not after, not by looking at the p-values and choosing a threshold that gives you the answer you want. Prefixing alpha is what keeps your family-wise error rate under control across all 7 tests. Alpha equals 0.05 is the conventional choice, and we will use it here. Fix the rule, then look at the numbers, never the other way around. With alpha fixed at 0.05 before we examine anything, we compute the critical t-value for the MSE degrees of freedom from the full model. Any effect whose absolute t-statistic exceeds that critical value is classified as active. Any effect below it is classified as inactive. Let us apply that rule to all 7 effects. Here is the annotated decision table. Temperature, A. Effect of 9.72, t-statistic of 13.2, p-value essentially 0. Active. Catalyst, B. Effect of 7.35, t-statistic of 9.95, p-value essentially 0. Active. The AB interaction, effect of 5.46, t-statistic of 7.39, p-value of 0.0001. Active. The AC interaction, effect of 1.77, t-statistic of 2.39, p-value of 0.0437. Active. Just clearing the threshold. Now the inactive terms. Mixing time, C. Effect of 1.27, t-statistic of 1.72, p-value of 0.124. Inactive. The BC interaction, t of 1.53, p-value of 0.166. Inactive. The three-factor interaction, t of negative 1.23, p-value of 0.253, and inactive for you. 4 active effects, 3 inactive. The decision was made against a prefixed rule, not by eyeballing and choosing a convenient cutoff. That discipline is what makes the conclusion defensible. Now we reduce the model. The logic is straightforward. Inactive effects are pulled into the residual, which increases the error degrees of freedom and sharpens inference on the active terms. But there is a constraint you must respect: the hierarchy principle. If an interaction is active, every lower-order term whose factors appear in that interaction must remain in the model, regardless of its own significance. The reason is interpretability. A model with an A-B interaction but without the A main effect is not a coherent description of how the factors operate. So the rule is, start from the highest order active interaction and work downward. Retain everything that hierarchy requires. Only then drop the remaining inactive terms. Never drop a main effect whose factor appears in a retained interaction. Let us apply this to the polymer experiment. Our active effects are AB, the AB interaction, and the AC interaction. The AB interaction requires A and B to stay. Both are already active, so no conflict. The AC interaction requires A and C to stay. A is already active, but C, mixing time, was classified as inactive. Hierarchy overrides that classification, because C appears in the active AC interaction. C must be retained in the reduced model. The terms we drop are BC and the three-factor interaction ABC. Those degrees of freedom are pooled into the residual. Let us see what that does to the model. Here is the before and after comparison. The full model has a mean squared error of 2.18 with 8 degrees of freedom in the error. The reduced model, after pulling the two inactive terms into the residual, has a mean squared error of 2.59 with 10 degrees of freedom in the error. 2 things to notice. First, the error degrees of freedom increased from 8 to 10. We gained 2 degrees of freedom by removing 2 inactive terms. Second, the standard error of each effect estimate decreased from 0.739 to 0.804. Wait, the SE went up slightly, even though we gained degrees of freedom. That can happen when the pooled terms carry some variance. The MSE absorbs a small amount of additional variation from the drop terms, which slightly raises the error estimate. But the gain in degrees of freedom makes the t-critical value smaller, so the net effect on inference is still favorable. The active effects are now estimated with more stable precision, and the model is simpler and more interpretable. That is the payoff for the discipline of model reduction. Let me summarize what the polymer experiment revealed. Temperature and catalyst concentration are the dominant active effects, large, clearly significant, and in the positive direction. Their interaction is also active, which means the effects are not additive. The benefit of raising temperature depends on what level of catalyst you are using, and vice versa. You cannot optimize them independently. Mixing time enters the model only because it appears in the active AC interaction. On its own, it is not a strong driver of tensile strength, and the practical recommendation is clear: to maximize tensile strength, increase temperature and catalyst concentration together. The interaction tells you that doing one without the other leaves performance on the table. Now it is your turn to work through the same sequence on a new dataset. A coatings laboratory runs a replicated 2 to the 3 factorial on paint adhesion measured in newtons per square millimeter. The three factors are surface preparation, factor A, primer type, factor B, and cure temperature, factor C. As before, each factor is coded to -1 and +1, and the experiment is replicated twice, giving 16 observations. Your tasks are compute the standard error of each effect estimate, run t-tests at prefixed alpha equals 0.05, classify each effect as active or inactive, apply the hierarchy principle to determine which terms must be retained, and refit the reduced model. Work through it before moving to the next slide. Here is the walked solution. The standard error for every effect is 0.067 again. A single value applies to all 7 estimates because the design is balanced. Surface preparation. A, effect of 1.69, t-statistic of 25.1, p-value essentially 0. Active. Primer type. B, effect of 0.788, t-statistic of 11.7, p-value essentially 0. Active. Cure temperature. C, effect of 0.238, t-statistic of 3.53, p-value of 0.0078. Active. Now the interactions. AB, effect of 0.088, t-statistic of 1.3, p-value of 0.230. Inactive. AC, effect of 0.138, t-statistic of 2.04, p-value of 0.0754. Inactive, just above the threshold. BC, effect of -0.062, t-statistic of -0.928, p-value of 0.380. Inactive. The three-factor interaction, effect of -0.063, t-statistic of -0.928, p-value of 0.380. Inactive. 3 active main effects, no active interactions. Hierarchy is straightforward here. Since no interaction is retained, all 3 main effects stand on their own merits, and all 3 are active. The reduced model keeps A, B, and C and drops all 4 interaction terms. The consulting deliverable is clear. Better surface preparation produces the largest adhesion gain, followed by the choice of primer and then cure temperature. All 3 factors matter. They act independently, and the recommendation is to optimize all 3 simultaneously.